Hey guys, welcome to today's Leetcode Contest. Let's get straight into it. I was able to solve all problems in today's 426 contest, and yeah, let's discuss them. Um, okay, we don't need this. Okay. So the first problem stated that um, we will need to calculate the smallest number x, which is greater than or equal to n, such that all the bits in the number are set to 1. So if all the bits in the number are set to 1, that means that number can be expressed in the form 2 raised to x minus 1, right? Because 2 raised to x is like all the bits are 0 and then only one bit is 1, right? So if you subtract 1 from it, you'll get a number with one less bit. So all the bits will be set to 1 in a number of this format, 2 raised to x minus 1. So that's what we have to check. We start from like x equals to x equals to 1, and then we keep going till we get this number is greater than or equal to n, right? And for the first number that we find such that it satisfies this equation, we'll just return the answer. So that's what we are doing. Int x is 1 and answer is 1. So while a is less than n, we keep multiplying x, and your a is actually your power of 2, which is x minus 1, and just return a. Okay. Let's go to the second problem. So the second problem stated that there are n minus 2 elements, there are n elements in a set, out of which like your n minus 2 are some random elements, and and then the n minus 1th element is the sum of all these elements. Let's say their sum is s, then n minus 1th element is s, and your nth element can be anything, and let's say it's lambda. And lambda can be equal to s, or lambda can be equal to any of these numbers. So let's say a1, a2, dot, or n minus 2. Lambda can be a1, a2, dot, or a minus 2. It can be, we don't care. So this lambda is the outlier. Okay, it's called as the outlier, and we have to find the maximum lambda, max lambda. Okay, so how to do this? So one trick that we can perform here is just take the sum of the entire array. Let's say the sum of the entire array is t. So t can be represented as s, which is the sum of the first n minus 2 elements. These are the special elements, right? S is the sum of special elements plus the number which is given, s again, right? Because there is at least one number which is the sum of all the elements, that is s, plus the outlier, which is lambda. So this is 2s plus lambda, right? So let's assume, now we will go through each element in the array, and we will assume that that element is the outlier, right? So for int e in array, let's say that e is my outlier. So that means that t minus lambda should be divisible by mod 2 should be 0, right? This is the first condition, because t is 2s plus lambda. So t minus lambda divided by 2 is s, right? T minus lambda by 2 is s. So in order for s to exist in the array, this has to be divisible by 2. And also we have to check if t minus lambda by 2 t minus lambda by 2 exists in the array. Okay, and is not equal to outlier. It's like, and its value, like its value doesn't coincide with the outlier. So outlier is lambda, right? So let's say in the edge case where t minus lambda by 2 becomes equal to lambda. So in that case, we would need at least two of them, right? So one of them would be the outlier, which is lambda itself, and another would be the actual sum, which is t minus lambda by 2. So we would need at least two of their counts, right? So So that's what we do. This is condition number 2, that we check if this exists in the array such that it is existing apart from the outlier, so that we can just maintain a frequency map. So that's what I'm doing here. We take a map of integers, we just calculate the frequency map, and we calculate the total sum. Now let's assume that x is the outlier, so I'll just straight up subtract that from the frequency map, saying that okay, I don't want to bother with the outliers frequency in the map, so I'll just update it I will just subtract it by 1. Then I check that if this sum is divisible by 2 and this frequency is positive, that means there's at least one element which is equal to the sum of these numbers, right? So if it is, then answer is just max of answer comma the outlier, which is x, else. And after all that, I again roll back the frequency and increment the frequency by 1, so just 2 plus plus fx, and we just return the answer. Okay. Question number 3. So question number 3 states that we are given some nodes in the graph, and we are given some nodes. We are basically given 2 trees, and we can add an edge between these 2 trees such that the distance between a target node and a given node remains less than or equal to k. So now, and we have to do this for every node in tree 1. Okay, so basically let's say this is your tree 1. Okay, and you have to connect a node from tree 1, and this is, let's say, your tree 2, okay, to any node in tree 2, such that the distance, this is 1, right? And let's say any of these nodes, so we have to basically count the number of nodes which lie at a distance of k minus 1, right, in this tree. And in this tree, we have to count the number of nodes which lie at a distance of are less than equal to k, and this is like less than equal to k minus 1, right? So how do we find, like, for example, if I want to calculate the answer for this node, I claim that it is always optimal to connect that very node that I'm trying to find the answer for to any node in the tree here. Like here, I will just do a brute force, and for this node, I will just do like, here the claim is that it's optimal to connect that very node, and let's say if I want to calculate the answer for this node, then I wouldn't go and say that okay, I'll connect this node to any of these brute force nodes in the tree, and that is because if we connect the node that we are trying to find the answer for, then there will be a direct connection to any of the nodes in the tree over here. Let's say this is your tree, right? The other tree. And the direct connection's length will be 1, which is the minimum length that is possible. And for that reason, we can just find like how many nodes are there, which is less than or equal to k minus 1. Right? Because it's just a greedy approach here to just find that what is the most optimal node that we can connect with another tree. And for example, let's say if I want to try to find the answer for this, but I connect this node to the other tree, like, so here what I'm saying is I'm increasing my distance by 1, right? And therefore here I want to find number of nodes which are at a distance of less than or equal to k minus 2, right? Because this is 1, this is 1, and then k minus 2 over here. So obviously the number of nodes which are less than or equal to, let's say these are the number of nodes which are less than or equal to k minus 1. So k minus 2 would lie somewhere over here, right? This is less than k minus 2. So you are reducing your own search space of the answer, right? And since you want to maximize the answer, we'll choose this search space. So that's why it's always optimal to connect from the node that you're trying to find the answer for. Yeah, so that's pretty much it. We just do a brute force. After that, we just brute force all the distances from all the nodes of this tree, right? Basically find distance from this node, this node, this node, this node, from every node. So you will have d of node. This is a 2D vector representing the tree distances. So let's say d1 of node from node in tree 1, and similarly d2 of node you will have tree distances like this. And these two things, less than equal to, less than equal to k minus 1, you can find from binary search. What you can do is, when you calculate these d1s and d2s, right, you can just sort the vectors, sort the distances. Since we don't care what the actual nodes are, we just care about the count of the nodes. So we just sort these d1 of, let's say, node and d2 of nodes, right, for every node. So basically each of these nodes will act as a root, right? And this can be calculated in O of n square, number of nodes square, because for one node it can be, for one node all the distances can be calculated in O of n. So for every node it can be calculated in O of n square, right? And you sort it and you just apply binary search on the nodes. Yeah, that's what I do here. This is my DFS where I just calculate the distances of the nodes, and here I make two graphs from the edges, okay, and then I have a distance vector. This is a 2D vector, okay. So this basically says that what are the distances if my tree is rooted at, let's say, node 3, 4, 5, 6 up till 1000, because the constraints start at 1000. So that's what I do here. I iterate over all the nodes in the graph. By the way, this set is n1. So n1 is the set of nodes in tree 1, n2 is set of nodes in tree 2. So I iterate over all the nodes in tree 1. I calculate the distance from all the nodes from x, right, like this. Just call DFS over here again and again, and yeah, I just sort the vector and then I insert the vector. So d1 of x becomes equal to d. And similarly I do it for the other tree, and then I just have an answer vector. And the answer vector, I'm saying that, okay, so for every node I will just make a connection from that particular node. So let's say this is my x that I'm iterating on, right? And the corresponding distances are, let's say, contained inside d1 of x, which is sorted, right? So d1 of x, so I want to calculate how many numbers are inside d1 of x which are less than equal to k, so that you can just do an upper bound, right? So that is up 1, and let's say your final answer is 0, and then you brute force on all the nodes in the second tree, and you just do an up 2, saying that how many nodes in, let's say, this can be a y, this can be a y, this can be a y, this is my tree 2, okay, like this, or like this is 1 1 1, right? So I just brute force over all of them, and I'll say that how many, if my tree is rooted at y, then how many of them, let's say d2 of y, how many of these nodes are distance k minus 1. So that's what I'm doing here, like just brute forcing, and then I just add different answer up 1 to step 2, and then just insert the answer here. Yeah, so that's problem 2. It was kind of a tricky problem, but yeah, it was good. Now problem 3 says that you have to do the same stuff without any k. So there is no k involved now. There is no k involved in the question, but we have to find the maximum number of nodes such that number of edges on the path from u to v is even. So we are doing the same stuff. We are connecting two trees with a node, but we have to, this time we have to find that how many yeah, this time we have to find out how many nodes are even lengths, right? So one beautiful thing to observe over here is that basically we have to maximize the count of the number of paths which are even in length. Okay. So one thing to observe is that, let's say you have a tree, okay, like these, and we know the number of even length paths from this particular node. We know the number of even length paths from this particular node. Okay. So let's say my tree looks like this, and here there is some nodes, there are some other nodes, blah blah blah. There's some other tree over here. This is a subtree. This is some other subtree. Okay. Let's say I pick a node in here. Let's say I call it n1. This is n2. This is n3. Okay. Now what will happen is that, and I know, let's say this is my root of the tree, and I know that I know d of n1, d of n2, and d of n3. Okay, let's say I know this. We know. So we just calculated this from the root node, which we initially fixed. Let's say the root node is, let's say, node 0, for example. Okay. And now I also know how many of them are even. Let's say this is an even number. Let's say this is odd, and let's say this is even, for example. Okay. And now I want to go and shift my root on this child. So I want to reroute the tree to this child. So how many distances will be even and how many of them will be odd again? So now my tree would look like this after rerouting. So this is my new root. Here a lot of nodes. This is my old root. There's one triangle over here, and there's one triangle over here, right? So triangle 1, triangle 2. Here you will have your n1 node. Here you will have your n2 node. Here you will have your n3 node. Here the distance of the edge is 1. So this was d1, and d of n1, right? This was d of n2, and this is my old root. Okay, this was d of n3. So what will change? So my d of n1, this is my new root. Okay, new root. So for new root, what will be the distance of n1? It will be 1 plus d of n1, right? We basically go from 1 and then just go from d of n1. D of n2 would be similar, like it would be 1 plus d of n2, and d of n3 would be d of n3 minus 1, right? Because d of n3 was in the way of the old root, so we just subtract this edge. So that becomes this at this distance, so d of n3 minus 1. So what happened to the parities of the distances? So all the parities will get flipped. So this was an even number, this will become an odd number. This was an odd number, this will become an even number. This was an even number, this will become an odd number, right? So all the parities got flipped. And now we again, let's say I want to reroute the tree to some other node inside the subtree. The parities will get flipped again. It will again become even, odd, even, and that this cycle will continue for any node. So essentially, what we achieved over here was that we can reroute the tree to any node, and we can, without actually finding the distances, we can know how many of these distances are even, how many of those are odd, by just doing one DFS, by just calculating the answer, the distances from the root. That's what we achieved, right? And this is a very critical observation to solve this problem, and that's what we will do here. Yeah. So from tree one, it is always optimal to connect the node from where we are finding the answer for, right? Because since it's just parity game, so it's here like it's saying that how many of these would be even, right? And from here, since here we have tree 2, we can just take a max of odd and even. So basically we want that the distance, let's say I connect to this node in tree 2, okay? So I want number of nodes which are at an odd distance, since this is 1, right? So 1 plus some odd number would be even, right? So that's why in tree 2 I want maximum number of nodes which are at an odd distance from any node. So here we established that the parities of the distances will just interchange. So I can just say that whatever is my max of even number of parities and odd number of parities, that I can connect that node to. Okay. So yeah, on the tree 2 it's sorted, but on tree 1 what node do we choose? On tree 1 what we will do is that it's always optimal to choose the node that you're trying to find the answer for. And the reason for that being that, let's say I'm trying to find the answer for this node, but I connected this node to any of the node which gives me like max of OE value on this node, on this tree, sorry. Okay. So here your distance would become 1 and 1. So your parities would flip, right? Here we need a distance of 2, so here you would be finding the node which would give the maximum even length, right? So that's again max of O and E. You can always flip the parities by doing this rerouting logic, alright? So the answer would basically remain the same. The claim is that the answer would remain the same because we're just flipping the parities. So it's always like, to avoid the headache, it's always optimal to connect this node for whatever we are finding the answer for. And that's what I'm doing here. I just take a graph. This is the same distance function, just build a graph, okay, and just calculate the distances from node 0 on both trees. And then I calculate the parities. So if it's an odd distance, I increment the odd counter from graph 1 or odd G1 or even G1. Similarly I do for odd G2 and even G2. And here that's what I do here as well in answer. So final OG1 is, let's say OG1, final EG1 is EG1. I iterate over all the nodes in graph 1 and I check if that particular node is at an odd distance, right? So let's say this is my 0 node and I'm trying to find the answer for this node. So let's say this node, okay? So this node is at odd distance, 1, right? So in that case, so it's like my parities would flip once. So even odd even, it would become odd even odd. And if my distance from the root was, let's say, at a distance of an even distance, let's say it was 2, then my parities would flip again. Like whatever the parities were, let's say even odd even, here let's say it became odd even odd. Here they will again become even odd even, right? Because they would flip twice. So basically it's, if it's an odd distance, you can flip the parities. If it's even, you can continue, you can take whatever was that you calculated. So if it's odd, right, you will just flip it. So final odd is the number of evens actually, and final evens is the number of odds actually in graph 1. And then we just calculate the answer. So answer of X would be number of final evens, right? Because we are interested in only the evens in graph 1, and maximum of odds and evens, right? Because we don't care what node we connect to in graph 2, because we can always flip the parities and we can just take the maximum of them, right? So that would be my maximum number of even parities in node graph 2. And then we just return the answer. yeah, so that was problem 4. Thank you guys for watching, and I know this was kind of tricky, and if you find, like, if you have any doubts, please feel free to comment. I will be more than happy to resolve them. Thank you.